Some reactions, like the explosion of rocket fuel, happen very quickly. Other reactions, like the gradual rusting of iron, happen much more slowly. The speed at which a chemical reaction takes place is called the reaction rate. To understand why reactions take place at different rates, let's take a careful look at how reactions occur. Chemical reactions occur when atoms or molecules collide. For example, consider the reaction of hydrofluoric acid with water to produce hydronium and fluoride ions. For this reaction to happen, the HF and H2O molecules must collide with each other. However, not every collision produces a reaction. The molecules must collide with enough energy and at an orientation that allows the rearrangement to take place. For example, if molecules collide in this orientation, a reaction will occur. But if they collide in this orientation, it will not. As an analogy, think about a bat hitting a baseball. The result depends on both the angle and the energy at which the bat and ball collide. In much the same way, the angle and energy of a molecular collision determines the outcome. Not every hit is a home run, and not every collision results in a reaction. Three major factors that affect how collisions occur and rates of chemical reactions include concentration, temperature, and energy changes. Because chemical reactions require the collision of molecules, the rate of reactions depends in part on how frequently collisions occur. When molecules collide more frequently, reactions occur at a faster rate. One way to increase the number of collisions is to increase the concentration of reactants. We can see this experimentally by reacting a metal, such as zinc, with hydrochloric acid. The dilute 1 molar acid reacts slowly with the zinc, gradually forming a few bubbles of hydrogen gas. By contrast, the more concentrated 6 molar acid reacts violently, quickly producing a large volume of hydrogen gas. A second way to increase the rate of a reaction is to increase the temperature. Recall that at higher temperatures, molecules move more quickly. Whether the reaction takes place in a solid, liquid, or gas, this means that the molecules collide more frequently. It also means that when particles do collide, they do so more forcefully, making it more likely that the molecules will rearrange. This is why we keep food in the refrigerator. Lowering the temperature slows down the chemical reactions that cause food to spoil. Energy changes also affect reaction rates. Recall that chemical reactions can be endothermic, absorbing energy from their surroundings, or exothermic, releasing energy to their surroundings. At first glance, the relationship between energy change and reaction rate may seem unclear. Many exothermic reactions happen very quickly, but others are much slower. For example, the reaction between sodium and chlorine is exothermic. The two elements react immediately and violently. The reaction of wood and oxygen is also exothermic, but the reaction takes place very slowly unless heat is added first. Although reaction rates are intimately connected to energy changes, the relationship is more nuanced than simple endothermic or exothermic descriptions. In order to understand this relationship, it's helpful to map the energetic factors that make reactions happen or prevent them from happening. This type of map, called a reaction energy diagram, shows the energetic changes that accompany a chemical reaction. For example, let's construct a reaction energy diagram for the reaction of hydrochloric acid with hydroxide. We know that the reaction is exothermic, as indicated by the negative enthalpy value. But does this reaction also require energy for the changes to occur? Let's think carefully about the reaction that takes place. In order for the hydroxide to take the hydrogen away from the chloride, there must be some instant when the hydrogen ion is pulled between the OH and the Cl, but is not fully bonded to either. This instant, called the transition state, is higher in energy than either the reactants or the products. The transition state is the highest energy arrangement of atoms that occurs during a chemical reaction. This arrangement lasts only for an instant, but it determines the energy hill that a reaction must get over. This energy barrier is called the activation energy. Along with concentration, the activation energy determines how quickly a reaction occurs. Even if a reaction will form a more stable product, if the activation energy is too high, the reaction will not take place. This also explains why many reactions require energy to get started. For example, you know that burning charcoal is exothermic, but it doesn't happen until you add a match and probably some lighter fluid. The match provides the activation energy in the form of heat to initiate the reaction. After that, the heat released by the combustion enables the reaction to continue. As a general rule of thumb, reactions with an activation energy less than about 40 kilojoules per mole occur at room temperature. Reactions with a higher activation energy require heating before they take place. A catalyst is a species that is not part of the balanced equation, but causes the reaction to go more quickly. A catalyst stabilizes the transition state in the reaction. This reduces the activation energy required to go from reactant to product. As a result, reactions are able to go more quickly. Catalysts are critically important in a wide variety of settings. In living creatures, compounds called enzymes act as catalysts to make complex reactions proceed quickly and with minimal energy cost. Manufacturers use catalysts to reduce the time, energy, and cost necessary to produce goods. Let's look at an example. Consider a simple reaction where compound A is converted to compound B. Based on the energy diagram shown, is this reaction endothermic or exothermic? Find both the activation energy and the net energy change for this reaction. The reaction diagram shows the energy of the substances involved. Because the energy of the product is higher than the energy of the starting material, the reaction is endothermic. The activation energy is the energy barrier that the reaction must get over in order to take place. The starting material has an energy of 40 kilojoules per mole, and the transition state has an energy of 140 kilojoules per mole. Therefore, the activation energy equals 140 kilojoules per mole minus 40 kilojoules per mole, or 100 kilojoules per mole. Because this activation energy is greater than 40 kilojoules per mole, this reaction will not take place without heating. The net energy change for this reaction is the difference between the starting material and the product. The net energy change equals 120 kilojoules per mole minus 40 kilojoules per mole, or 80 kilojoules per mole.